Hi everyone, welcome to another episode of the Common Lisp Study Group. I'm your host Ram Vedam with Atlanta Functional Programming. Um, Today I was trying to prepare for our discussion on the last piece of our coding challenge on extending students parser and students solver to actually solve system of equations, and I ended up encountering a situation that I realized was actually solved inside um, the simplification version of the Symbolic Mathematics program in Chapter 8. So, in lieu of actually solving that, and uh, I thought it would be great to start talking about that chapter anyway, and then at the end, go back and probably finish up the system of linear equation stuff along with probably other stuff on uh, whatever comes in the chapter 8 exercises so we can hit, two birds with one stone. So I know a lot of folks looking at the title of this talk and maybe the book um, chapter might be thinking, why is symbolic mathematics getting some sort of degree or even some sort of discussion in a book on artificial intelligence? Well, most people who were born in, when I was growing up in the 80s and 90s, um, up until even early 2000, that is, know somewhat of the history of how symbolic mathematics actually started. And it was very much in the guise of artificial intelligence and artificial intelligence research. Originally, remember, computers were designed to, as the book kind of went through, kind of were specifically designed to perform numerical calculations, right? Large scale arithmetic, addition, subtraction, multiplication, division, computing trajectories of ballistic missiles, as you know, for military applications, large mechanical mainframes. Everybody knows about the glorified Hollywoodization of some of those stories, whether it be um, Enigma and the works of the great Alan Turing, or even some of the stuff regarding how the uh, first, personal computer came about, and some of the researches are going on later on from there. But what most people don't know is from the success of Enigma and from the success of the military applications that happened in post-war, a lot of folks ended up adopting and using and even pushing through the guise of artificial intelligence the ability to solve more mathematical equations of the kind that most of us are familiar with from reading in school, like whether it be algebraic equations, stuff that we saw in student, or integration and derivations and large scale multivariate calculus problems, right? A lot of these stuff were actually created in the 60s and 70s, and many of us did not actually encounter this. It was only much later, and I'm sure any of you who are living through the 90s remember those graphing calculators. It was much later. I think it was late 70s that early 80s that graphing calculators started even showing up to actually give you the kind of functionality that you would typically get for symbolic mathematics that you would get in these large scale mainframe computers. Um, and I'm not even talking about, symbolic mathematics programs like the large scale ones that most people are aware of for most. And if you're not, some examples are Mathematica, which comes out of Wolfram Research. There's a program that the book mentions that I didn't even know existed called Derive. Everyone knows MATLAB for Matrix Laboratory for MathWorks. There is also Math Lab, okay, as in mathematics laboratory. Um, and there is another symbolic thing that's somewhat unknown for most people called Maple that is still heavily used too as well for symbolic integration and such on. A lot of these programs were developed and used by professional mathematicians and physicists to solve large-scale scientific problems, right? And but it's interesting to note that some of these techniques that was used to actually be put into these problems came from the AI space, particularly in the early days when they were looking into dealing with symbolic algebra in the first place. A couple of programs that the book brings up, one of which I again I think most people may not be familiar with, was the program Saint that was created in 1963. That's basically using a search technique like GPS in order to actually provide um, solutions to different problems. And it had this interesting feature of being able to backtrack while it's working through particular problems when it fails that the search actually didn't actually conclude into a derivation or a result to the particular integration problem. And again, you'll see when we start playing around with this maxima variant today that more on that. The successor to that, of course, is the um, a program called Sign, spelled SIN, that was using the same techniques, but they actually incorporated and hard coded a bit of mathematical knowledge that pruned the search tree in order to actually go and solve the particular problem, thus removing the backtracking feature that Saint originally had. And that did make the performance of Sign much faster than Saint. But when a wrong answer or a wrong choice was going to occur where it couldn't just simply solve a problem, instead of trying different techniques, it'll just say, I can't solve it. Um, that actually was further refined with some work by a person called R. Reich, has what the book describes to create what ultimately is probably one of the first, I think, computer algebra systems. That is the Maxima program, which is also part of a DARPA grant that came out to create a computer algebra system, and especially one that computes symbolic algebra. Um, Maxima is still used today, technically, although I don't know to what extent. I know it's available in its entirety open source online for folks to go and download and try out. Um, but as far as the community is concerned, because we are only mainly incorporating new algorithms and you're not advancing kind of the science of um, or even leveraging a lot of techniques that are normally associated with artificial intelligence, um, and more importantly, they're refined numerical algorithms. Maxima is no longer actually considered to be part of the AI space, and a lot of actual symbolic algorithms and symbolic algebra systems are not considered artificial intelligence programs anymore. But we should actually um, revisit Maxima and some of the techniques. And one of the reasons why it's incorporated in this book is because the same early techniques that we used up until now to actually go and solve word problems and, in Eliza's case, tried to create conversational dialogue systems, that same technique can be applied also to solve symbolic algebra problems, especially when you are talking about algebra um, that is somewhat more one of the equational, I guess it's probably the correct way of sort. And this is some of the stuff that, if you recall, we were trying to actually adjust um, student to do anyway. Maxima is a big program. This is by no means going to be a full-blown deep dive into how Maxima works at all. I mean, from what I read in the chapter, I think it is even simpler than what Maxima actually does in terms of techniques for solving problems. Today, specifically, we're going to be exploring some of the basic stuff that this Maxima simplification program that you see up in front of you, that's part of the PAIP repository, this actually goes through and given an equation, its goal is to actually go in and provide a simplified form of the equation that's provided to you. Now, obviously, for many people, simplified can mean many things, right? Depending upon the application, right? If you're talking about simplification from the standpoint of, you know, into differentiation, one form of a equation might be better than another form. I'm assuming most of you are familiar with the quadratic formula um, and have seen something of the form just right here, you know, x plus a x plus b versus x squared, sorry, ax squared. No, it's x squared plus ab a plus bx plus ab. Um, in some cases, the left-hand side is preferable if you're trying to find roots of the equation, because if you're doing the quadratic form, if you had it in the second equation, you have to remember the quadratic formula for finding roots, which hopefully most of you are familiar from your high school algebra class. Whereas if it's in the simplified form there, if you know by looking at it, oh, this is just x plus a plus x plus b, you can find the roots very quickly. It becomes minus a minus b. One of the things to recognize in that is that what is the actual uh, simplifications that we're actually going to deal with. And this particular program is dealing with somewhat um, what Norvig calls simpler simplifications. So they're obvious simplifications, things that you do automatically, right? When you are looking at a particular equation and before you get started solving it. Most of the obvious simplifications can be done using the already popular and hopefully somewhat repetitive for folks who've been following the series, rule-based approach for actually simplifying an equation. Okay, so we've already talked about rules in Student. We've already talked about rules in ELIZA. How would such a rule look like in um, the maximum program? Well, I think it's first important for us to actually go and talk about what um, Norvig was talking about in his section call on how he was defining the fully parenthesized syntax versus the um, operator precedence rules, and we need to kind of make sure that we understand um, the difference between um, the two. Okay, so most people are familiar when we start talking about. And hold on, I think it'll be better if I pull up a scratch buffer here. Um, okay. 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 So when we start talking about, simplifications versus operator precedence versus what Norvig calls fully parenthesized infix notation. Okay, it's important to note what he means by this. Now, before I begin on this piece, one more thing for those who are just joining us and want me to kind of clarify. Um, yes, this program is going to be fully in fixed notation. We are going to be dealing with first converting something that's in fixed notation that's pretty typical that you would see in a computer algebra system or anybody who's writing stuff in natural mathematics to a prefix notation, something that Lisp will understand, and eventually we'll change it back to infix and we'll be going through the differences between there. But in order for us to do that, we need to understand what the difference is between what's a equation that's fully parenthesized versus an equation that deals with operator precedence, and which approach are we going to actually leverage and deal with today. Um, so I'm just going to kind of talk briefly about this for this, and then postpone, given the time, the actual discussion to um, how this is solved, hopefully with the time remaining very quickly. Maybe it might go into next time, but we'll see. Um, okay, so take a look at these two equations, all right? A times x squared, okay, plus b times x plus c, okay, versus something that looks like the following. A times x squared plus b x plus c, okay? And even this one versus our standard one that most people are familiar with, right? Um, with or without parentheses, it doesn't really make much of a difference. Um, and this is straight out of for a second for reference, the chapter 8 figure. What was the figure again? It was I'll just say chapter 8 page 256, I believe it is. Okay, for those who are following along in the book. Okay. Now there's one more, with or without. So number 6 can also be written without parentheses, but it doesn't make a difference. Now the first one is fully parenthesized in fixed notation. Why is it fully parenthesized in fixed notation? Well, remember, infix notation is talking about two operands with the operator for the operands in between. Okay, and in the first example, we've essentially explicitly defined the associativity of the equation. Okay, that's why you see the outer parentheses on top of the left-hand side and the right-hand side. Furthermore, we also further restricted the associativity between the times and the plus. Okay, and we know the order in which we're doing this. Okay, so in here we know that we would first compute x squared, which is x to the second using the exponential. Then we'll multiply that by a, while we're also going to deal with the um, multiplication of b times x. And then we take that together, add that to c. Okay. There is nothing ambiguous about this equation. All right. Everything is explicitly defined. You always go into the parentheses, you evaluate the parentheses, and you go in or out. So you find the innermost parentheses that you can evaluate, and you evaluate from the innermost and go out, okay, to compute the answer. This is different than what most people are familiar with which is operator precedence. I'm sure most of you have not forgotten PEMDAS, which is the acronym that most people talk about when they talk about operator precedence. Okay, parentheses, exponents, multiplication, division, addition, and subtraction. And the second example actually illustrates that. Without parentheses, we know the order of operations of the actual equation that's being presented here, all right? And so that actually brings up then which one is the correct approach that we should be doing, or which one is the one that the book takes? Well, given how ugly um, but let me talk about also the third one. The third one is essentially operator precedence, but it also takes advantage of something that most people um, use in written notation, which is implicit multiplication. We assume that if two terms are next to each other and they're different terms, then it's automatic, or even they're the same term, they're automatically multiplied to each other if there's no operator in between them. Okay, this is just some standard notation that's written in textbooks that you write on. Um, and The fourth notation that I completely forgot to point out here is the one that requires you to write a custom parser to break it into appropriate Lisp pieces. Okay. Um, Lisp symbols. So if we wanted to actually deal with what we currently have and reuse what we have, we're going to have to look at each one of these approaches slightly differently and then think about which one to apply. And I'll just kind of give you the answer. So the um, the fully parenthesized case, um, if we want to handle the fully parenthesized case, we might first try to essentially use prefix to infix that we've used in the previous case here, which is, let me just pull it up here. I think it's an augs function. Yeah, I think it's an augs functions. Yes. Prefix to, no. It's going to be in student. Give me a second here. We might try to use students code to actually go in and translate this, okay? Um, which is pretty interesting. It will go in and map the binary expressions and then grab the left-hand side, right-hand side, and create the actual operator, and then return a list in this case of the actual binary expression that's being created. And then the the infix to prefix notation will be somewhat the same, but it's interesting. If you look at prefix to infix and you think about infix to prefix, which is what we need, infix to prefix is nothing more than taking the call to prefix to infix, and it will actually convert if we use the fully parenthesized case, that is this case, and we'll convert that into an appropriate expression. Let's see how this happens, and because I believe that that is the technique that we're actually going to end up that was used um, by Maxima in the first place. All right, so let's go back to Maxima, not simple Maxima. Okay, so now if we look at prefix to infix, we're using the same operation, same code that we've done before. Okay, let's go ahead and first load this. Requires maxima. Okay, all right. So um, so let's see how this looks. Okay, so if we do prefix to infix, and let's just try that ax squared stuff that I just see. Let's just see what just happens. Okay, so we do a times x squared plus ooh, plus b times x plus c. And let's see what happens. Oops. Right. I have to go in. I forgot. Okay. I'm sorry. Give me a second here. Quit. Thank you. All right. I forgot to put this as a quote. And plus C. That's what I want to do. And no. Wait a second. Forgot one more parentheses. Plus C. There we go. You can see that by doing the fully notation, we'll end up getting plus ax squared bx plus c. Okay, and everything kind of fits into it. So they didn't have to do any change when it was put. But if we try doing prefix to infix on, and that's just infix to prefix, by the way. So what we created here is technically infix to prefix. So if we look at infix to prefix in the expression, it's going to ultimately call, based on the infix rules, the prefix rules that we created. All right. Now, what's interesting is while this works, okay, the book actually ends up, and the implementation actually ends up improperly implementing operator precedence. All right. And the reason is one, well, you guys can see the prefix fully parenthesized infix notation, writing code like that or even equations like that, it's very ugly because it can and more importantly, if you don't count the number of parentheses when you're writing the associativity, you might end up doing what I did earlier and trying to actually add them all into a single form, which is fine for Lisp, but for other symbolic algebra, most people, if you're trying to do it, you're trying to specify associativity, it you need to kind of provide that. So, um, So I wanted to show you just to illustrate why this is a problem. If you do prefix to infix on this, and you'll see what happens when we do, and why the book ended up using operator precedence. You do bx plus c, you'll get that. And that's because of the fact that it doesn't have any understanding of, it can't treat the expressions, right? It doesn't know what those expressions are that we just kind of showed. So in order to do infix to prefix correctly, what we do is we create a database of rules. All right, these are your infix rules. All right, using the same pattern matching stuff that we talked about last time. Okay, and what it does is it creates its database to actually go through the rules, search through the rule-based translator based on the rule pattern response, and it can converts the expression, if it's not an atomic expression, based on these rules, to the appropriate prefix form. So you can see, like, if you see x plus equals y plus, that means that equals xy, and so forth. It will, just convert them into what we expect. Now, these two we're not going to actually probably touch base on today, but this one is for integration and then derivation. Well, derivation integration, respectively. We're just going to mainly focus on the arithmetic stuff for the time being, just so that you have an understanding on how that stuff is, and then we can start talking about, at least briefly, um, I think it's in section 8.3, after the section on associativity, commutativity. We talk about, it talks about the derivation pieces of the actual program. I want to dive into that a little bit, but I haven't had a chance to be quite honest. So I will, just, leave it at that. Okay, so how does this guy work? Well, let's see what happens when I just simply change this guy to to lookup. Okay, infix to prefix, and we run this. You can see that it does exactly what we are expecting. Well, slightly, in that it actually went through the tree and then created appropriate subtrees of the left-hand side being ax squared and the right-hand side being the addition of b times x plus c. Now, what's interesting here, I just realized, is there's a mistake, and that is I have to put a space in between them, otherwise it actually is not doing what we expect it to. Now it's actually correct. Spaces are important in this program mainly because it doesn't ignore spaces. Spaces have to be, I mean, it are significant in terms of positional stuff for the translator to actually understand what it's looking for. And you would have to write basically a lexical analyzer to go and make sure you insert the spaces before you run through this if you want to actually support what most people end up writing when they're writing their code the first time. So a couple of things I kind of skipped before we started talking about is I mentioned the rule-based stuff because we've seen it so many times. But I want to bring up, just to make sure that most people who are just joining us aren't aware of, what the rule structures were again. Just brief, a brief review. So from student, we actually extracted the rule representation that the student uses. So we have the notion of an expression that contains essentially a left-hand side and operation, a right-hand side. You can make an expression using the make exp constructor that we've defined right there on line 19. We have a couple of utility functions to determine whether or not we're dealing with an expression. We have a predicate function that we grabbed from student as well. That is the binary expression. Of course, we've already covered prefix to infix that we grabbed from student too. The other thing I want to also briefly mention is uh, there's two additional pattern matching abbreviations that you've probably seen earlier that when I first introduced the rule-based stuff that's important that I didn't cover. That is, we need to have an idea of a sequence. So in order to create that, we have a couple of special sequences for um, x plus and y plus in order to make sure that you can define these sequences. What are these sequences? This is um, this is so that we can actually potentially define the sequence of characters that are representing a actually I think if I remember correctly it's for symbols. So if I do this and do running, yeah, it's so that we can actually extract full symbols from a particular thing. One thing to note though, for the simplification algorithm, my understanding, at least when I was looking at this code and reading the book so far, was that we have this variable predicate that checks to see if we have single letter variables. So even though our infix to prefix stuff actually handles the symbol stuff correctly, the simplifier that's written in Chapter 8's implementation of Maxima does not actually cover uh, these symbol sorts of stuff for simplification and actually other features of the system. Okay. Um, After that, I mean we could talk simply on this, but I'm just going to show one more piece of information here that I think it's important to recognize, because there's two things in um, the the program that is important. One is before we talk about the simplifier, that is, one is, well, we looked at um, how we're constructing rules. We looked at the simple infix to prefix database, but then but for certain rules, especially certain mathematical or arithmetic rules, there are certain axioms that you need to follow. Like I think everyone remembers the identity rule for addition, which is x plus 0 equals x. And since plus is a commutative operator, since um, most people are aware, you need to write it as not only x plus 0, but 0 plus x. So you have to make sure that both ways are equal to the final value. Um, the addition of two values, x plus x equals 2 times x. Okay, you want to kind of remember that. Um, x minus 0 equals x, and then 0 minus x equals minus x. So there's a bunch of these simplification rules that we know ahead of time that is important to be aware of, that I think uh, we need to first take a look at. Okay. Oh, so let me pull up that too as well. Um, wonder, did this actually have? Okay, interesting. I'm actually surprised it didn't show up. Okay, let's do this. So he separated the rules from the actual notation. Okay, so one thing to be aware of for is this thing. This is probably new to all of us in this study group, which is defining a new operator like this, um, and then doing conversion. Um, anybody knows, everybody knows that in Common Lisp, it's pretty lax on the idea of keywords and symbols and stuff. I mean, there are keywords in that if there are functions defined in the standard library and the symbol already exists inside of the Lisp image, you'll be able to you could throw an error. But things like these operators don't necessarily exist inside of common Lisp. And specifically for infix notation, when you have something like this x, y, you could see that. Oh, and I just noticed one more thing that. Let me pull this one up example one more time. Okay, if we do that, perfect. Okay, so let me reiterate this piece again and show this to you. All right, so if you look at this equation here that we see here, this prefix notation introduce effectively a function called it doesn't exist. Okay, then that is the caret symbol. That defund there, line 79, is basically converting that function call into an exponential stuff so that it can be simplified further later on, or it can be evaluated. This is before we actually go into the set of simplification rules, which is dealing with all your standard arithmetic rules that most people are familiar with. Yes, for those who are paying attention with the keen eye, it did define x divided by 0 correctly as undefined, and 0 to 0 as also being undefined. Um, and all these other rules are, I think, familiar for most of you. I don't have to go through all of them here. But these identities are necessary because when you're running the simplifier, what the simplifier does is it actually takes in the equation, converts it to infix notation, and then uses these rules to effectively figure out um, what is the actual simplification expression that you need to deal with. Um, and what's important to note is that there's two different pieces here that I'm still kind of wrapping my head around, because there's simplify expression using the search stuff here, and then this simplification for a function, simplify function that I need to kind of still revisit and understand. But once you understand these two, then simplify, the top level simplify is actually pretty straightforward. So if you look at simp, which calls simplify, and simplify, all it's doing is it's gonna check to see if it's an atomic expression. If it's not an atomic expression, it's gonna go and try and simplify the expression, but it only simplifies the expression after we've currently took every expression and simplified um, that given expression. So this is how you would end up writing the recursive case. So it'll go through the tree and simplify everything, and then it'll traverse back up. Um, just to give you guys a quick demo of this, let me just see if I think I have to do maxima R first, and then wait a second. Oh, wait, two. My apologies. I tried to use load. It has there we go. Let me see if I could do simplify. Let's see. Let's try a simple equation. X times x plus x plus x plus 1. Right. And the reason is because I forgot to put a space in between the times again from a habit. Okay. If I do that, ooh, it did not do what I had expected it to. So this is telling me that infix to prefix may have failed. Well, let's see. Yes, I forgot to do infix to prefix. So in order for me to do this, we have to first do infix to prefix. Okay. Then we have to call simplify. And it did exactly what I expected it to. Okay, so let's look at what this full thing does. We have to actually run the simplifier program to get the REPL. So if I do x times x plus x plus 1, it should actually do, what the heck? Ooh, it did not do what we expected it to. Let's try. Let me see something. Maybe I messed up how we actually call this program. Oh, thank you. I have to actually, I forgot that I have to actually provide parentheses. There we go. So now you see that it's going to return the fully parenthesized version of the actual equation. Same, one more example here, obviously, that would be useful is x y plus xy plus y times y. You'll see, okay, this doesn't handle, I forgot, this doesn't handle uh, implicit multiplication yet. X times y plus x times y plus y times y. Okay, x. Ah, so it didn't recognize that you could do a further simplification there because it doesn't recognize that because it's using fully parenthesized notation, right? So okay, so this is very somewhat limiting, and this is something that we may need to fix in the exercises. But if I do x times, let me see what happens if I do this times y. Okay. Okay. So this at least works. Now, one thing that we need to also make sure if I do that, obviously for most people, let's make sure that we do correct things. And this is something that we're probably going to have to cover next time. But this is, in its current iteration, I don't believe, yeah, in its current iteration, it does not actually handle commutativity and associativity. And this is something that we'd have to also deal with. I'm actually surprised. Oh, I think if I just simply, wondering if I could just say x times y equals y times x here. Fix that very quickly. Let's see. X times y equals y times x. We may need to do an abort. Okay, rerun it. Now, okay, so let's see here very quickly. Did I actually fix it? Or did I make it worse? Yes, I made it worse because it we need to handle associativity. So there's a still a bit of a deep dive in this program that we need to go through to understand the associativity and commutativity piece. But that's going to take over time. So this is kind of the brief top level introduction to our. Okay, so we have a question. Thank you for this. Why do you choose 8 for starting? Oh, so for those who are just joining, I chose chapter 8 for starting because while I was working on chapter seven's final piece, um, I realized that the solution that I came up with required me to simplify an expression. Um, to, and at least the approach that I was taking to actually create something that's a substitutable expression to create a linear equation of a single variable. So to reduce essentially multivariable, multiple unknowns into a single unknown using substitutability. So, and it turns out that I could probably use a similar technique that we're doing in effectively the maxima example to actually go and solve that piece too as well. So I could hit two birds with one stone. So I decided to cover um, the chapter 8 material, which is on symbolic mathematics today. Um, Other questions? Okay, well, I know this is a brief introduction and it's a start, but next time when we cover, or when we continue, we'll be covering associativity, commutativity. Um, we'll also deep dive into the evaluation rules here and how the simplifier actually does the lookup. But I'm pretty sure most people have probably figured it out by now. And we will also be talking about um, we might have time to also start talking about how do we potentially extend this stuff or talk about through uh, the what's it how to extend maxima for logarithms, trigonometric functions, differentiation, so forth. Um, Again, these are all using the same search techniques that we have up till now. And we're also going to have time, hopefully next week, we'll cover the final two pieces, which is the rest of Chapter 8, which is also dealing with limits of rule-based approaches and integration, but we'll see how far we get. So without further ado, I appreciate you all joining me on this lovely Monday evening. I hope you guys have a fine rest of your evening and a great coming week. I will see you guys next week.